What if I told you that chopping down a single tree in the middle of the Amazon doesn't just impact local carbon capture, but can actively alter the rainfall over a farm on an entirely different continent?
It's wild to think about.
It really is. I mean, when we look at a map or, just look out the window at an empty lot, we tend to think of land as a passive surface.
We're at like a stage.
Exactly, a stage. It's just the dirt we build our houses on, or the
Yeah.
space we pave over for a highway, or I guess the soil we plow to plant crops. And we usually view it purely in terms of real estate or area,
Right.
right? Asking ourselves, how much space is left.
Yeah, that's the standard view.
But today, we are doing a custom deep dive into a stack of academic reading notes. And these are based on the 2023 Planetary Boundaries Assessment.
Mm.
And our mission today is to completely dismantle that passive view of the ground beneath our feet. We're looking at the planetary boundary known specifically as land system change. And to help visualize this, I really have to point out the digital display you've set up in your workspace today.
Oh, yeah.
It's this incredibly dynamic, shifting projection of the Earth. But the continents look, I don't know, incredibly dense and wild.
Yeah, it really changes how you look at the planet, doesn't it?
It does.
What you're seeing on the display is a scientific model of historical Earth ecosystems. This is during the Holocene era.
Okay.
It's a projection of the planet's baseline potential. So basically, this maps out what the global forest cover and biomes would theoretically look like under stable Holocene-like climate conditions.
Right, before we got involved.
Exactly. Before widespread human agricultural and industrial intervention, it has the baseline we use to measure how much of the Earth's active breathing machinery we've actually altered.
Wow. See, I'm struggling to visualize how we even begin to measure that. So, okay, let's unpack this for a second. Looking through the notes, the scientific community's approach to measuring this boundary has changed drastically.
Very drastically, yeah.
Because back in 2009, when the Planetary Boundaries Framework was first introduced, the control variable, the metric they used to see if we were in the danger zone, it was just the percentage of global land that had been converted into cropland.
Right. Just measuring the farms, basically.
Right. But by the 2015 and then the 2023 updates, they threw that out entirely.
Mm-hmm.
They shifted to measuring the amount of forest cover remaining compared to that Holocene potential you have on your display there.
Yes.
And I'm trying to wrap my head around why they abandoned the cropland metric. I mean, was the 2009 method like trying to measure a patient's overall health by only counting how many calories they eat, whereas the 2023 shift to forest cover is like monitoring their actual heart rate and blood pressure?
Well, that's a good way to put it.
Like
Yeah.
we finally started measuring the actual systemic functions.
That analogy works perfectly, but the reality is almost even more urgent than that. Akin to discovering the patient's internal organs are actively shutting down, not just, tracking their diet.
Oh.
Yeah. If we connect this to the bigger picture, using cropland as a proxy in 2009 happened mostly because it was relatively easy to track via satellite.
Oh, sure. You just look for the giant squares of corn.
Exactly. But the scientific community quickly realized that measuring human expansion doesn't answer the core question,
Which is,
has humanity changed these systems so much that the Earth can no longer maintain a stable climate?
I see.
Because land isn't just a passive floor. Vegetation, and specifically dense forest cover, it actively exchanges massive amounts of carbon dioxide, oxygen, and water vapor with the atmosphere.
Right.
Forests alter the aerodynamic roughness of the Earth's surface, which actually dictates wind patterns.
Wait, really? The wind?
Yeah, the physical friction of the trees changes how wind moves globally. They are physical thermodynamic regulators. So cropland expansion was missing the actual mechanical functioning of the Earth system.
Right, because converting a tiny specific sliver of a highly climate-sensitive forest might permanently disrupt global weather patterns, whereas paving over a much larger area of a different, less critical landscape might only have, local effects.
That is exactly it. That is the core realization that drove the change in the metric. The boundary needed to focus on the biophysical processes that influence the climate far beyond the actual physical location of the trees.
Okay, that makes a lot of sense.
Yeah, and forests are the heavy lifters for these processes.
Yeah.
But, and this is crucial, the planetary boundary framework doesn't treat all forests equally. The forest workforce is highly specialized based on geography.
Yeah, I noticed that in the breakdown of the biomes.
Mm-hmm.
The planetary boundary is separated into tropical, boreal, and temperate forests,
Mm-hmm.
and they've completely different jobs. The notes say tropical forests act as the Earth's water recyclers,
Right.
But how does that actually work mechanically?
So it operates through a massive biological pump called evapotranspiration.
Evapotranspiration.
Yeah. Tropical trees have these deep, deep root systems that pull vast quantities of groundwater up into their canopies. And then the intense heat of the tropics causes that water to evaporate from the leaves, transpiring into the atmosphere.
Okay, so they're sweating, basically.
Basically sweating, yeah. And by doing that, these forests are essentially manufacturing weather. They create atmospheric pressure systems that pump moisture inland, forming what scientists call flying rivers.
Flying rivers, that's an incredible image.
It is. So a tropical forest isn't just sitting there passively receiving rain. It is actively generating the rainfall that sustains agriculture thousands of miles downwind.
That is mind-blowing. So if you're drinking a cup of coffee right now in London or New York, the stability of the price of those beans, that relies on that moisture recycling in the tropics.
It absolutely does.
But that brings me to a genuine point of confusion here. I'm looking at the notes on boreal forests, the dense northern woods in places like Canada and Russia.
Right, the boreal biome.
Yeah. If the tropics are manufacturing weather through intense heat and evaporation, what on earth are the freezing forests doing? I mean, they certainly don't have the solar heat to evaporate massive flying rivers of water, right?
No, they don't. What's fascinating here is that boreal forests do an entirely different job for the planet, and it's centered on energy and light.
Light?
Yeah. They regulate the Earth's surface energy balance through the albedo effect.
Albedo, like reflectivity.
Exactly. Albedo is just a measure of reflectivity. So imagine a barren, snow-covered landscape in the far north. It has bright white, meaning it has high albedo.
Right.
It acts like a giant mirror. It reflects incoming solar radiation right back out into space, which physically cools the planet.
Oh, I see. But when you have a dense forest of dark green or brown pine trees standing above that snow.
They act as solar sponges.
Solar sponges.
Yeah. Those dark, dense boreal canopies absorb the solar heat instead of letting the snow reflect it. So if you remove those northern forests, or, say, if climate change causes them to expand further north into the tundra, you drastically change the thermal dial of that entire hemisphere.
Wow.
You alter how much solar energy the Earth retains versus how much it bleeds back into space.
Man, it changes how you look at a forest entirely. It's not just a habitat for animals, it is a physical piece of climate infrastructure.
It really is infrastructure, yeah.
But understanding how vital these systems are makes the actual numbers in the 2023 report highly confusing to me.
How so?
Well, to stay within the safe operating space, the boundary dictates that tropical forests must remain at 85% of their potential Holocene cover.
Right.
And boreal forests also have to stay at a strict 85%. But temperate forests, the ones we see across much of the U.S. and Europe, they are allowed to drop all the way down to 50%.
Yeah, that's a big gap.
It's a huge gap. Why does a forest in Germany or Ohio get such a loose boundary, while a forest in Brazil or Siberia is held to a rigid 85%?
It comes back to the overarching mission of the Planetary Boundaries Framework. This framework is not a general measure of ecological goodness, or local conservation.
Okay.
It is strictly evaluating global Earth system stability. So temperate forests absolutely matter on a local level. They hold immense biodiversity. They prevent soil erosion. They filter local watersheds.
Sure, they're super important locally.
But their specific biophysical influence on the global climate is mathematically weaker. Their removal doesn't trigger a violent destabilization of the global climate system the way, shutting down the moisture recycling of the tropics or altering the energy balance of the boreal forests does.
Okay.
The 50% boundary just reflects that lower global leverage.
I see. So if those are the strict rules, 85% retention for the crucial regulators and 50% for the temperate zones, how much wiggle room do we actually have left before the climate machinery starts to break down?
We have zero wiggle room.
Zero.
Zero. The 2023 assessment confirms the land system change boundary is fully transgressed. We are operating in the high-risk zone right now.
Oh, man.
Yeah. Globally, we are at about 60% of potential forest cover when the safe global boundary is aggregated at 75%.
Okay.
And those temperate forests we just discussed, they have been cleared so extensively over centuries of human development that they are currently down to about 30%.
Wow. So we are failing across the board.
Unfortunately, yeah.
But here's where it gets really interesting, because the source text stresses that we have to look past those top-level percentages.
Mm-hmm.
There's a massive distinction drawn between land conversion and land degradation. And this completely shatters the illusion of just, sending a satellite up to count the number of green treetops.
It really does.
Because conversion is obvious, right? That's clear-cutting a forest to build a shopping mall or a massive soybean field.
Right, you can see that from space easily.
But degradation is much sneakier.
Degradation is the silent dismantling of the machinery. You can have a piece of land that is technically classified as forest, but its ecological function is entirely broken.
Like how?
Well, this often happens through selective logging, or when industrial infrastructure fragments a continuous forest. The most glaring example, though, is the commercial pre-plantation.
Okay.
You might clear a rich, old-growth native forest and replace it with a single-species, fast-growing tree plantation. And that's designed to be harvested for timber or paper every 20 years or so.
Right. So to a satellite snapping a picture from orbit, that plantation registers as green.
Exactly.
It looks like a forest cover.
Yeah.
But it's missing the deep soil microbiome. It's missing the complex root structures that actually infiltrate the groundwater, and obviously the biodiversity of the original system.
Right, it's completely hollowed out.
It's like a real estate developer tearing down a vibrant, diverse neighborhood and putting up identical, empty concrete housing blocks.
Oh, that's a great analogy.
Technically, a drone looking down would categorize both as housing. But the community, the economic interaction, the actual life of the area is completely gone.
And worse, those concrete blocks often require massive external inputs just to remain standing. Much like a monoculture plantation requires chemical fertilizers and pesticides because it lacks natural resilience.
That makes total sense.
This highlights exactly why the planetary boundary indicator is essentially a measure of the extent of forest systems, but it cannot be mistaken for a complete measure of forest integrity.
Right. They aren't the same thing.
No. High canopy cover can mask incredibly low ecological integrity. That's why scientists vehemently warn policymakers against using this planetary boundary simply as a raw pre-planting target. You cannot just plant 1 billion pine trees in a straight line and claim you've restored the Earth system.
Right. It doesn't work like that. Well, if the data is this deceptive, we need to look at what is actually driving this change on the ground. The reading notes list agriculture, livestock, timber extraction, mining, and urbanization. And livestock makes sense mathematically given the sheer land mass required for grazing pasture and, growing the feed crops.
Huge amounts of land.
But urbanization stood out to me. The total global footprint of cities is actually relatively small compared to agriculture, but we tend to build our cities in the absolute most ecologically sensitive bottlenecks, right? Like coastal estuaries, river corridors, rich floodplains.
Exactly. We build where the resources flow. But the true complexity of these drivers is actually found in global commodity chains. The bulldozer clearing the land in one hemisphere is almost always fueled by consumer demand in another hemisphere.
Which brings up a specific driver in the notes that genuinely shocked me, and that's the bioenergy paradox.
Oh, yes. The paradox.
We are constantly told that shifting away from fossil fuels toward biomass, like planting fast-growing crops or trees to harvest for energy, we're told that's a crucial green solution.
Right.
Wait, how is that a green solution? Who is writing a policy that encourages chopping down an intact native forest just to plant a row of crops for ethanol or wood pellets?
It's a huge problem. And this raises an important question about how we design environmental policy. It illustrates perfectly the danger of looking at planetary boundaries in isolation.
What do you mean?
Well, planting biomass for energy is heavily incentivized by climate policies because, in theoretical carbon accounting, burning a plant for energy is considered carbon neutral.
Because the plant absorbed carbon while growing and releases it when burned.
Exactly. But those accounting systems are deeply flawed. They often fail to account for the carbon released from the soil when the native land is cleared in the first place, or the loss of future sequestration from the old-growth forests.
Oh.
So you end up with government subsidies that make it highly profitable to clear vital climate-regulating ecosystems just to plant fuel crops. The effort to solve the climate change boundary actively destroys the land system change boundary.
It's a systemic paradox. The attempt to save the atmosphere destroys the terrestrial machinery regulating it.
Exactly.
And the notes ground this in some very concrete case studies from India that show the mechanics of how these drivers operate locally. Take the city of Bengaluru.
Right. Great example.
Rapid urban expansion. There isn't just an aesthetic loss of trees. The notes detail how replacing soil with impervious surfaces, concrete and asphalt, it fundamentally breaks the water cycle.
It does. Let's trace the mechanics of that. When a drop of rain falls on a healthy peri-urban forest, the canopy slows it down, and the complex root system acts as a sponge, right? Channeling that water deep underground to recharge the local aquifer.
Okay, so it captures it.
But when you pave over that recharge zone, that same drop of rain hits hot asphalt. It immediately evaporates, or it turns into flash flood runoff, picking up pollutants along the way.
Right.
The aquifer depletes, and simultaneously, the loss of shade and transpiration creates a massive urban heat island, raising the local temperature by several degrees.
That is just brutal.
Mm-hmm.
And the other India case study focuses on the Western Ghats, which is this incredibly biodiversity-rich mountain range.
Mm-hmm.
And the issue highlighted there isn't just the sheer volume of deforestation, but the fragmentation.
Yes, fragmentation is key.
Because when you drive highways, dams, and transmission lines through a continuous forest, you slice the ecosystem into isolated islands. The flows of water, the migratory routes of species, the genetic diversity, it all just breaks down.
It completely breaks down.
The total area of trees might technically remain high, but the ecological connectivity is severed.
And fragmentation introduces what we call edge effects.
Edge effects.
Yeah. The interior of a deep forest has its own microclimate. It's cooler, more humid, protected from high winds. But when you cut a road through it, you expose those sensitive interior species to dry winds, harsh sunlight, and invasive species from the edges.
Oh, wow.
The forest literally begins to dry out from the inside. And importantly, there's a heavy justice element intertwined with all of this too.
Right, because the notes ask a critical question. Who benefits and who bears the cost of this land change?
Exactly.
A forest cleared in the global south to grow a commodity export might boost national GDP or lower the price of goods for a consumer thousands of miles away in Europe or North America.
Yeah.
But the local indigenous or rural communities, they face immediate displacement.
Right. They lose access to non-timber forest resources, clean local water, and they face heightened vulnerability to extreme weather.
And the consumer driving the land conversion never has to live with the ecological fallout.
Never. Which underscores why a purely mathematical approach to conservation fails. You cannot mandate a top-down lockup of global land without addressing procedural fairness. A just transition requires recognizing the stewardship of local communities, providing alternative economic livelihoods, and frankly, addressing the historical responsibility of industrialized nations who already cleared their own forests centuries ago.
Wow. Okay. So we understand the flawed metrics, the hidden degradation, and the economic drivers pushing us over the limit. Which brings us to the most unsettling part of this deep dive. We've transgressed the boundary.
We have.
So what actually happens to the Earth when we push it entirely out of its safe operating space? Have we fallen off a cliff?
Not exactly. The scientific consensus carefully distinguishes between a boundary and a tipping point.
Okay, what's the difference?
Crossing the land system change boundary does not mean the Earth's ecosystems collapse instantly on a Tuesday afternoon.
Right, it's not a movie.
No, it is not a binary state of safe versus doomed. The boundary represents a gradient of escalating risk. It is risk management positioned.
I see. So crossing the planetary boundary is like, it's like driving on the highway with severely bald tires in a rainstorm.
Oh, I like that.
You haven't necessarily crashed the car yet, but your risk of losing control is exponentially higher.
Yes.
And the actual tipping point, the regime shift the scientists warn about, is when the car actually hydroplanes and spins out.
That is an excellent way to frame it. The boundary tells us we are driving on bald tires. But tipping points do exist within these biomes, and they are driven by self-reinforcing biophysical feedbacks.
Okay, like a chain reaction.
Exactly. The source text points to the Amazon rainforest as the primary example of a system approaching a regime shift.
Okay, can you walk us through the exact mechanics of that feedback loop? Like, how does a rainforest actually dismantle itself?
It starts with the disruption of that moisture recycling we discussed earlier.
The flying rivers.
Right. When human activity causes large-scale deforestation in the Amazon, the regional capacity for evapotranspiration drops. Less moisture is pumped into the atmosphere, which leads to a localized, extended drought.
Okay, that makes sense.
But that drought severely stresses the remaining intact trees, making them shed leaves and dry out. This dramatically increases the landscape's vulnerability to fire, which is a naturally rare occurrence in a healthy rainforest.
Oh, because everything is usually so wet.
Exactly. But now it's dry. When fires inevitably break out, they cause mass tree mortality. That mortality results in even less canopy cover.
Which reduces moisture recycling even further.
Yes, triggering a deeper drought. It becomes a runaway loop where the ecosystem transitions from a lush rainforest into a dry savanna entirely on its own, regardless of whether humans cut down another tree.
And as that system crashes, it takes the other planetary boundaries down with it. The loss of habitat slams the biosphere integrity boundary. The altered runoff and failed aquifers hit the freshwater boundary. And billions of dying trees release massive reserves of stored carbon, accelerating the climate change boundary.
Yes.
This is a catastrophic domino effect.
It is. And the 2023 Earth system modeling makes this undeniably clear. The planetary boundaries interact. Climate change and land system change continuously reinforce one another.
Right.
The consequences of transgressing one boundary dictate the resilience of the others. We cannot treat them in legislative isolation.
So what does this all mean for us? I mean, we've diagnosed this systemic risk, but the notes acknowledge a very stark reality. 8 billion people need food, housing, and infrastructure.
We do.
We can't just pause human development. How do societies navigate back to a safe operating space? The text explicitly states that simply relying on efficiency won't save us.
Right. This is a classic economic trap. It's often called the Jevons paradox.
The Jevons paradox.
Yeah. Technological solutions like precision agriculture, better fertilizers, or highly efficient irrigation are crucial. But if that increased efficiency simply makes farming cheaper and more profitable, the economic incentive is to clear more land to maximize those new profits.
Oh, right, because it's suddenly cheaper to do it.
Exactly. The total pressure on the boundary doesn't drop. It expands. Efficiency without limits just accelerates the degradation.
Which means we need a fundamental system transformation. The notes actually tie this directly into a framework called donut economics.
Yes, donut economics.
I've heard the buzzword thrown around in sustainability circles, but how does that actually apply to land management?
So, imagine a donut consisting of two concentric rings. The inner ring represents the social foundation of human needs. We require agricultural land for daily caloric intake, timber for housing, space for infrastructure.
Right, the basics for survival.
We cannot allow populations to fall into the hole in the middle, which represents deprivation and poverty.
Okay, I'm with you.
But the outer ring of the donut represents the ecological ceiling, the planetary boundaries we've been discussing. Donut economics is the challenge of designing supply chains, diets, and agricultural systems that operate entirely within that sweet spot.
In the actual dough of the donut.
Exactly, meeting the foundational needs of humanity without overshooting the biophysical limits of the Earth's machinery.
But, to make this tangible for the listener, if someone is commuting right now or sitting at a desk prepping for a meeting, why should they care about the biophysical limits of the outer ring?
Because land system change is the invisible architecture dictating the daily realities of your life.
How so?
Well, the stability of agricultural yields affects the inflation at your grocery store. The paving of recharge zones dictates whether your local municipality will face water rationing next summer. The loss of regional transpiration influences the severity of the heat wave you'll experience in July.
That brings it right to your front door.
It really does. I would urge anyone listening to look at their immediate surroundings today, whether it's a suburban subdivision or a commercial farming district, and ask themselves, what used to be here? And what invisible ecological functions were sacrificed to build this?
That is a phenomenal grounding exercise. As we wrap up this deep dive, I want to sincerely thank you for guiding us through the complexities of biome boundaries, the danger of the bioenergy paradox, and that incredible Holocene model on your display.
It was my pleasure.
We started this journey trying to understand how land is more than just a passive surface, and I think we've definitely uncovered the mechanics of the machinery.
It's been great exploring it with you. But, before we sign off, there is one final lingering thought embedded in the core logic of these academic sources that I think we must confront.
Okay, let's hear it.
The entire premise of this land system boundary relies on measuring our current degraded forest cover against the potential forest cover of the Holocene.
Right, the baseline.
It asks what could grow under stable Holocene-like climate conditions, but as we've established, the climate change boundary is already severely transgressed.
Yeah, we're past it.
The Earth is rapidly moving out of Holocene-like conditions. So if global temperatures permanently shift the thermodynamics of the planet, permanently altering what can biologically grow where, are we measuring our survival against a historical ghost?
Wow.
Does the potential baseline itself move, trapping us in a metric we can never physically achieve again?
Are we measuring our survival against a ghost?
What an absolute mind-bending thought to leave on. As you go about your day, let that question sit with you. and keep questioning the ground beneath your feet. Until next time.